Alright, so logistic, not logarithmic, logistic growth. In exponential, so that's a different kind of growth. In exponential growth, we assume the rate of change of increase or decrease is directly proportional to the population. So it just increases like crazy or decreases like crazy. Like particularly the population of Clark County in the 90s and 2000s. So, but that's not normally maintained forever. So what happens is a lot of times that there's a limiting factor, and so that growth tends to top out for some reason. So you can think about in Las Vegas, there could be water issues, there are land issues because we have Red Rock to the west and Lake Mead to the east, and the bombing range, Nellis bombing range to the north. So we could grow to the south all the way down to the California border, but there's still going to be some limiting factors of what the population can be. And so that could be limited there also. So L is called the carrying capacity, so we want to pay attention to that. That's going to be right here. So you can read that yourselves. I think it's just easiest to look at an example and see what we might have to do with a question like this. All right, so we have a population of fish in a lake, and it follows this logistic differential equation here, where t is measured in years, and we also have this initial condition at p of 0. So if we take a look at this, what we can do is factor out, there's a p in here, and we can get rid of this, we notice there's no fraction here, so we want to get that out of the way. So if we divide by 1 over 6,000 times p, then we would be left with 3 divided by that is 18,000. So that would be 18,000 minus p. All right, that's the differential equation. That's the derivative with respect to time. So if we want to find the limit of the actual function, the limit is L. It's in there. So it's whatever that number is. We don't have to use any of our limit tricks or anything like that. It's just the L from that formula. So the trick we used actually was to factor out these other things, so we would just be left with L minus P. Okay. What is the range? Well, it tells us that we started at 4,000, so we have 4,000 there, and then the maximum is going, the limit is going to be 18,000. Okay. Now, if you think about it, if we want to know where something is increasing, we look at where its derivative is positive. So that is the derivative right there. And if we set that equal to 0, so I don't want to write that out again, I'm just going to put dp dt equals 0. And so that would be when p equals 0 or when p equals 18,000. So back to the good old days of AB. We would do a little sign chart here, and that's 0, and this is 18,000. But we're not really going to test that section of the values because it doesn't even go that low. And I don't even want to plug in something. I need to get closer to 18,000. So let's try 10,000, because we want to consider that 4,000 cutoff also, actually. So let's just try 10,000. So we put 10,000 in there. Those are both going to be positive. And then if we put 19,000 in there, then this would be negative times a positive, so that would be negative. So if you think about why might the population of fish in a lake start to decrease after a large increase, and so maybe they introduce fish to this lake and the population starts going crazy, and then they start eating all the food in the lake, and so then the population maximizes out there. There's a maximum number of fish that are going to be able to live in a lake. All right, so the question was, what is it, increase or decreasing? So it's going to be increasing from for what values of the population? So that's going to be from 4,000 to 18,000. Okay, because dp dt is greater than 0. And it's going to be decreasing from 18,000 because dp dt is less than 0. Alright. Now, for what values of p is the solution curve concave up and concave down? So that's where we need to look at the second derivative. So if we're going to take the second derivative here, what we want to think about is where, if we go back to the first derivative, it would be easier to use, if we're going to take the second derivative, it would be easier to use this equation to find the second derivative. So the derivative of that is just going to be 3, but then that's going to be dp dt. And then that is going to be minus 1 over 6,000, and then p, and bring the 2 down, so it's going to be 2, so that's going to be 1 over 3,000. And then that's also going to have a dp dt. So what we can do is factor out this 1 over 3,000. We can do that first. So we're going to factor out 1 over 3,000. So we're going to have 1 over 3,000, and then we're going to have dp dt, which we could factor out both of those. So that's going to leave us with 9,000 minus p. Now, dp dt is up here, and we factored it to this also. So now if we think about our sign chart again, so now we're going to have this added value of 9,000 here. So really I want to start this off at 4,000 and 9,000 and 18,000. And if we check that second derivative out for those values, so if we plug in 5,000, this is going to be positive. And actually we need to test it up in here too though. Remember this, I just didn't want to write it all out again. All of this is right here. So we have all 3 of these values we have to worry about. So if we plug in 5,000, this is going to be positive, this is going to be positive, this is going to be positive, so that's going to be positive. And then if we plug in 10,000, this will be negative, positive, positive, so that's going to be negative. And then if we plug in 20,000, this is going to be negative, this is going to be negative, that's going to be positive, and negative times negative is positive. So we have that. So we have concave up from 4,000 to 9,000, and unified with union with 18,000. Infinity seems a bit much, but technically. And now I almost forgot, because the second derivative is greater than 0. And then we're going to say concave down from 9,000 to 18,000 because it is less than 0. Alright. So remember, an inflection point is when the second derivative changes sign. So yes, at p equals 9,000 because the second derivative changes sign. And the population is defined. There's not going to be a vertical asymptote with respect to the population. Use the information you found to sketch the graph. So it looks really similar to that graph I had at the top of the page, actually. So except we would want 4,000 here, and 9,000, and 18,000. So kind of have a horizontal asymptote here and here, and we have an inflection point at 9,000. So that's where it's going to kind of switch directions right there. All right. So this is basically the same equation here. The only difference is our initial condition has changed. So when we factor that, we're still going to get 18,000 here. But now the range is going to be 10,000 to 18,000. All right. So again, when is it increasing, decreasing, etc.? So that changed at 9,000. So you can flip the page back if you need to and look at it. But so it was positive after 9,000. So that means that this is going to be increasing from 10,000 to 18,000 because this is positive, which we found out in example 1. It's not decreasing anywhere because that happened before 10,000, if you remember the points from that. Okay, and similarly, if we think about where is it concave up or down, that was between 10,000 and 18,000, this is going to be negative that whole time. So it's concave. I guess I could use red since I used red on the other side. So it's concave down from 10,000 to 18,000 because second derivative was less than 0. Okay, does it have an inflection point? No, because no sign change in the second derivative on the interval. And sketching a graph of that. So here we've got 9,000 and we have 18,000. And this graph is starting at 10,000, so it's starting right there. And we still have the same limit to growth if we factor this out. And we can do that, I suppose. That's going to be 1 over 6,000 p, and then that was 18,000 minus p. Okay, so our limit to growth is still 18,000, our carrying capacity. So that just goes up like that, basically. All right. So now, this is a little bit awkward here if we look at this one. So again, we have that same situation, except now the initial population is 20,000. If we factor that out up top, it's the same. This is the same. So the limit, the carrying capacity, is still 18,000. Now the range is going to be 18,000 to 20,000. Okay. Now, when we passed 18,000 on the other side, so I just decided to recreate that over here again. There's the same formula over and over again, but here's the sign chart. So if we plug in like 17,000, that's going to be 17,000. That's going to be positive. That's going to be positive. So that'll be positive. Plug in 19,000. That'll be negative times positive. So that's going to be negative. Okay. So for what values, it's not increasing ever because we're only going from 18 to 20. So it's negative in that whole time. So it's going to be decreasing from 18,000, it's a little bit sloppy, 18,000, to 20,000 because dB dt is less than 0. Okay, concave up or concave down. So if you look at the second derivative, we had those choices. It was a little bit longer equation. It was that, and then it was times 9,000 minus p. So, I guess we could show that. So that's going to be 1 over 6,000 times P times 1,800 minus P. I'm going to check just to make sure. So that was 9,000. Another 1 over 3,000, which is not going to affect much. And then 9,000 minus P. Okay, so if you think about those numbers, we're focused on 19,000, in between 18,000 and 20,000. So 19,000, that's going to be a negative, times a negative is a positive times a positive. So that means that it's going to be concave up from 18,000 to 20,000 because the second derivative is greater than 0. Okay? Does it have a point of inflection? No, because from 18 to 20, if you need to draw the sign chart again, you can, but, and I didn't even draw it here. Oh, here it is up here. So from 18,000 on, it's going to stay positive the whole time. So, no, because no sign change in second derivative in the interval. Probably wouldn't hurt to actually give the interval either, 18,000 to 20,000. Alright, and use your information to sketch a graph here. So now we have 18,000, we have 20,000, and there is our limit, and this is going to start at 20, and it's going to go down like this. Okay. Alright, so this isn't going to be that important, I don't think, but we'll go ahead and try to fill this out anyway. So if you look back to our notebook on page 130, Larson, section 5.5, you'll see that we had a logistic function that looked kind of like this with the limit to growth of the carrying capacity in the numerator. And then we had, I don't think we talked about it exactly like this, but we had an expression in the denominator. We didn't really break it down to its parts, I don't think. So that L there is the same carrying capacity that we just did on the previous examples. Now, from here, if we want to switch this to dy dt, we would have k times y, and then we would have times L minus y. Okay? Now, k and L are constants, positive constants. So now the general solution to that would be separation of variables. So we would bring all the y parts, divide both sides by that. So that would be dy over y times L minus y equals k times dt. And then we would integrate both sides. Now in pre-calc, you may have done partial fraction decomposition. If you don't remember that, I'll be going over it. We're going to be doing that again when we integrate. But basically, you're taking this fraction here, 1 over y times L minus y, and you separate that because these are linear terms. That's all we have to do there. And we haven't covered that yet, so I'm going to leave that there. But we could continue, break that down, and then take the integrals of each of those parts. But we can make a connection between this equation and this equation down here. And what we want to focus on are some of these variables. So k right here is the same as this k right there. Alright? And the L here are the same as those two L's right there. So let's think about what this would look like. So if we use the formula P of 0 equals 5, so if we plug 5 in for y and we plug 0 in for t, then this is going to be 1 plus a e to the 0. And now we want to know what L is. We can use this to find L. So if we factor out this, so that would be 0.0002, and we could factor out a p, and that would leave us with 100 minus p. Okay, so that's L right there. Now, K, if we compare this to this up here, then that's our K, to match those K's. And our L's to match those L's. So, like I said, this isn't really that big of a deal, so if you feel a little bit overwhelmed there, don't worry about it too much. So we're going to solve for a here. So we're going to multiply both sides by this. So that's going to be 5 plus 5a, e to the 0 is just 1, so I don't need that, equals 100. And then if I subtract 5 from both sides and then divide by 5, I'm going to get 20 minus 1, which is 19. So we have the answer to this question already, actually. What's the limit as it approaches infinity? It's going to be 100. Alright, but the formula is going to be 100 over 1 plus 19e. And remember, it's L times K. So K is 0.0002 and L is 100, so you move that over 2 places. So that's going to be negative 0.02 t. So that would be our formula there. Now, for these other versions here, that will also be 100, and that will also be 100. All we'll be changing is the value of a. And if you're curious and you want to work those out, this A will end up being 2/3, and this A will end up being negative 1/6. Okay? And I'm not really worried about which one has an inflection point, so because like I said, it's not that important. So I just want to wrap this up with this last example. So here is our K. And here's our L. So 50, so that's going to be 50 equals, L is 3,000, so that's going to be 3,000 over, and then we're going to have 1 plus A e to the 0 again. So if we multiply that, that's going to be 50 plus 50A equals 3,000, very similar to the problem up here. And similarly, I'm going to not subtract the 50 into that. I'm going to leave it and divide by 50. So A is going to be 60 minus 1, which is 59. Alright? So solve for P as a function of T. That's what we did up here. So L is 3,000 and A is 59, and K times L is going to be, that's 1 over 1,000, so that's 3. So that's going to be negative 3T. Alright? So it says use your formula there to find the population at 2 days. So you would just plug in 2 there. So that would be 3,000 over 1 plus 59 to the negative 6th, which is 2,617.240. Okay, find the number of days that have occurred when this flu is spreading the fastest. So if we want to find the maximum rate when it's the fastest, what we can do is take the derivative of the rate and find out where it changes from positive to negative. So that's similar to what we did in the very first example, I think, in this section. So if we take the second derivative of that, that would look like this. And again, it would be easier if we separated that back through. So that would be 3p. That would be 3p minus 1 over 1,000 p squared, because it's easier to take the derivative of that. So that's going to be 3 dp dt minus 1 over 500 dp dt. So if we factor that out, that 1 over 500, that's going to be 1 over 500 dp dt, and then that's going to be 1,500 minus p. Okay, so we can do a chart on that. That's going to be 1,500 here, 3,000 here. The 3,000 and the 0 come from this, because that's what dp dt equals down here. So we also have these two factors. So that's where we're getting 0 and 3,000 and 1,500. So if you plug in 1,000 here, this is going to be positive, that's going to be positive, that's going to be positive. So those are all positive. If you plug in 2,000, positive, positive. If you plug 2,000 here, that's negative. Okay, so what we can see is that the rate of change is its derivative, the second derivative, there's a maximum when p equals 1500. So if we plug in 1500, we can solve this right here, which was 1 plus 59 e to the negative 3t. And if you can use the solve feature on your calculator, that's approximately 1.359 days. Like I said, this whole lesson is not that important, so you shouldn't be too stressed out about it if it's giving you a hard time, but mostly we're just plugging stuff into a formula. So the rest of this is an odd lesson, so don't let it get you down. All right. It's about that time.